Today we're going to push forward a little bit. We move from equations describing motion to graphs that describe motion. On the board right now you see 5 examples of what we call position time graphs. I want to point out to you first, before we analyze these specific graphs, that any graph is always going to be titled whatever the y-axis is versus the x-axis. So these ones are all called position time graphs because the y-axis is position and the x-axis is time. Does that make sense? We'd never call that a time position graph. We'd always call it position time because it's always y-axis versus x-axis. Now, the other thing that I want to point out to you is that the x-axis of your graph is always the manipulated variable. The manipulated variable, and the y-axis of the graph is always the responding variable. Do you guys remember those terms? Have you seen those before? The manipulated variable and the responding variable? Sometimes you call them the independent variable and the dependent variable. Have you seen them called that? Have you seen them called manipulated and responding though? So you've seen it called both then. Okay, we'll always use the terms manipulated and responding, but if you have seen the terms independent and dependent, the manipulated would be the independent. And the responding variable, the one that responds to the manipulated variable, would be the dependent variable. This is the last time that I'll use those terms, independent and dependent variable. We're always going to talk about them as manipulated and responding variable. So any graph has the manipulated variable on the x-axis, any graph has the responding variable on the y-axis, and any graph is titled y-axis versus x-axis, or in this case, position versus time. Now, what I want to do with each of these graphs is to describe what each of these shapes represents. We have in graph number 1 a straight line on a position time graph. You guys know what position is, right? Position is where something is, the location of something. In this graph, you can see in the first graph, the position is changing. It's increasing, right? You're moving. Because it's a straight line, what do we know about that changing position? It's constant, right? It's changing at a constant rate. In other words, we would say this is constant velocity. In fact, we'd say it's constant positive velocity because my velocity isn't changing and you're going in the forward or positive direction. Constant positive velocity. What do you think that second graph represents? It's also a straight line. Is it also constant velocity? Is your hand up? No? Oh, sorry, I thought your hand was up there. Yeah? Yeah, it is constant velocity in a sense, but it's specifically a constant velocity of 0 value, right? Look at it. The position isn't changing. So we're going to say this object is stopped. Now, you could technically say, because it's stopped, it's a constant 0 velocity, because it is, right? It's constantly 0 velocity. But it probably makes more sense to say that it's just stopped, or you could say no motion. Anything like that would work. Now, the third one, it's also a straight line. Is this a constant velocity? Yes. Yes, it is. This one, though, you can see the position is decreasing. So you're getting back closer to where the reference point is. We would say this is a constant negative velocity. What does that really mean? It doesn't mean necessarily that you're physically going backwards. It means you're going back to the starting point. So let's say Okotoks is our starting point. We're driving from Okotoks to Calgary. Then we would say my velocity is positive. If I was driving from Calgary back to Okotoks, my velocity is negative. That doesn't mean that I'm in reverse, that I'm backing up from Calgary to Okotoks, Okay, I'm just traveling in the negative direction. If Okotoks is 0 and Calgary is positive 20, then I'm driving from Calgary back to Okotoks, my velocity would be negative. And if I'm going at a constant velocity, we'd say it's constant negative velocity. What do you think the fourth one means? Yeah?
It means that you are not traveling at a uniform rate, which means you have acceleration.
Yeah, you're accelerating, you're speeding up. You could say acceleration means the same thing as increasing velocity. Okay, it's got a certain steepness right here, a certain slope right here. It's got a steeper steepness or slope right there, even steeper right here. So what's happening? Well, it must be speeding up. If the slope is increasing like this, then it must be speeding up. And the word we use to describe speeding up is usually acceleration. And the last one? The fifth one, sorry? That's not a constant velocity because it's not a straight line. This is slowing down or deceleration. Look, we got a pretty steep one right here, but then it decreases in steepness. So if it decreases in steepness, it doesn't mean that you're not moving. It just means that you're slowing down as you're moving. Okay? Look, we're going from this and getting closer to this, right? Steep, and then it kind of evens out pretty much flat. So we're slowing down. We're going from constant positive velocity to being stopped. So we're slowing down or we're decelerating. Deceleration. Now, some of you are going to just memorize the shapes of those graphs. I'd rather you not memorize them. I'd rather you look at each graph individually on its own and figure out whether it's accelerating or traveling at a constant positive velocity or decelerating or stopped, or whatever the case may be, based on some of the things that we've mentioned here, right? Like slope is decreasing in the last one. Oh, it must be slowing down. The position is staying the same in this one. In the second one, oh, well, if the position is staying the same, it must be stopped. So figure those things out. There's enough stuff to clutter your brain. Now, there's enough stuff that you've got to remember, that you've got to memorize in all your subjects to fill up your brain. Okay, don't try to memorize anything you don't have to memorize. Figure stuff out if you can. It takes a lot less brain space, or at least it seems like it takes a lot less brain space. What if I was to give you another one? You don't have to write this one down if you don't want to. What if I was to give you this one, position versus time? The graph looks like this. Again, you don't have to write this one down if you don't want. Yeah, good. It's impossible. How come it's impossible? Because you're going back in time, right? This is why I want you to not necessarily remember those graphs, but to be able to figure them out, to understand them. Because if you remember them, well, then you're probably not going to get this one. If you understand them, then you're going to be able to figure that this one is, well, look, time is increasing, and then what's happening to time? It's decreasing. You can't go back in time, right? So this is completely impossible. What about this one? You don't have to write this one down either if you don't want to. Position versus time. Hey, what's my manipulated variable here? Time, because it's on the x-axis. Okay, what about this one? My graph looks like this. Yeah, you can't do that one either. How come? You're going from one position to another position, and no time has gone by. Ever watch Star Trek? Like it's like teleporting, right? It's teleporting from one position to another position with no time having gone by, which it's actually been done with what we call photons, these tiny little particles of light. Scientists have actually teleported little photons of light from one position to another position with no time having gone by. But for all intents and purposes, this is impossible. Okay? In the everyday world, this is impossible. No person has ever been teleported. Okay? Sorry?
How far did they teleport?
I have no idea. I have no idea. And I also don't know, like, how they know it was the same photon, for instance, like, you know, that they were looking at, right? But I don't know the details of it, but they must have had something, obviously, to do that. All right. Now, we want to get a little bit more detail-oriented with these graphs. Okay, you see a graph up here now, or at least a x-axis and a y-axis. Let's label them position and time. What's my manipulated variable again? Time. What would I title this graph? Position time, or we could say position versus time. Doesn't really matter. As long as position comes first, time comes second. Sometimes you might even call it position as a function of time. As long as position comes first and time comes second. Yep. Now, I'm going to draw this such that the graph looks like this. Just a simple straight line on this graph. Actually, let's change it just a little bit. Let's draw it so that it looks like this. You want to find the position on a position time graph. Well, I'll tell you what. It's the same as finding the velocity on a velocity time graph. Or it's the same as finding the acceleration on an acceleration time graph. Or it's the same as finding the force on a force versus time graph. Or momentum, whatever the heck that is, on a momentum time graph. Whenever you want to find the variable that appears on the y-axis, and position is the variable that appears on the y-axis, right? All you're going to do is go up and over. Up and over. So if you want to find the position at this moment in time, right here, then we would go up and over, and we would read the position right there. Does that make sense? Easy. Like, it's the easiest thing possible. As long as you understand what we're doing, it's the easiest thing possible here. You want to find the position on a position time graph, up and over. You want to find the magnetic flux on a magnetic flux versus time graph, then you're going to go up and over. Okay, whenever you want to find a variable that appears on the y-axis, you're going to go up and over. Even if you don't even recognize that graph, like magnetic flux versus time, for instance. Now, what about displacement? What do we define displacement as? Change in position. So if you want to find displacement, well, you're going to find position twice, and then subtract them, right? So you're going to go up and over twice, and then subtract. So there's a position. Hey, here's another position. Up and over, and then we're going to subtract those two positions in order to get displacement. We can call it displacement, but what you're really finding here is the change in position. If you wanted to find the change in velocity on a velocity time graph, up and over, subtract the velocities. You wanted to find the change in magnetic flux. That's actually kind of an odd term, actually. I'll use a different one. You're not going to understand why that's odd right now, but you want to find the change in momentum, let's say. On a momentum time graph, get momentum by going up and over again, and then subtract the two. Average velocity on a position time graph. You guys are going to answer this one for me right now. You know this. The average velocity on a position time graph. How do I do that? Yeah?
You find two positions, and you find your displacement,
Yeah.
and you divide by the space in between.
Yeah. Guys, that's what we've been talking about for the last 2 days, right? Velocity is displacement over time, right? Right, that's what your quiz is on Friday. Displacement over time. Now, the displacement we get from right here, right? So we're kind of going in a progression, right? Position leads to displacement, and displacement leads to average velocity. Now, there's another way to find average velocity here if it's a straight line, but it really boils down to the same thing. The change in position over the change in time is really the same thing as saying rise over run. So this is really just the same thing as saying the slope. I prefer to think of it, to be honest, for me, as displacement over time, as opposed to slope. But if you want to think of it as slope as rise over run, that's fine. Yeah. Yeah, that's a good question. That's a really good question. Will we be given the direction for this? Usually, yes. So usually that would say position to the north or something like that. But if you're not, in the absence of being given a direction, when you're looking for velocity, what it means is that, well, you can always assume that, is that the direction is the positive direction. That may mean north or it may mean south. But whatever it is, we're making it positive.
Okay.
Does that make sense?
Yeah.
So there is a direction, north, south, east, west. We may not know what it is, but whatever it is, we're going to define it as positive.
Okay.
That's a good question, really good question. Now, to find the instantaneous velocity on a position time graph. What does that mean, instantaneous velocity? That's a big word. Yeah, like let's break the word down. Instantaneous, instant. The velocity at one moment in time. Not the average over the trip, but the velocity at one instant. And the good news for this is that it's going to be the same. That is, if we have a straight line, if it's a straight line, then the instantaneous velocity will be the same as the average. Now, we're going to see tomorrow situations where it's not a straight line. But if it is a straight line, and that's all we're going to deal with today, then we're going to say the instantaneous velocity is the same as the average. Let's think about that. Let's say that the average velocity on this graph was 5 meters per second. Let's say. If the average was 5 meters per second, and we know that a straight line represents constant velocity, then the velocity rate here, everywhere at every instant in time must be the same. So it must be 5 meters per second. The instantaneous must be the same as the average. Does that make sense? Okay. What I'd like to do right now, before you pack up, is take a look at one example that you see on the front side of one of the handouts that you got a few minutes ago. What's the position of the object in the graph to the left at 10 seconds? At 10 seconds, how do we do that? Up and over. Up and over looks like it's 30 meters. What's the displacement between 0 and 10 seconds? Well, my position right here at 0 is 80 meters. And then at 10 seconds, it's 30 meters. So the displacement will be up and over, and then subtract the two. It's going to be 30 meters minus 80 meters, which is negative 50 meters. Now, somebody, I can't remember, who was it that asked the question about the direction? Okay. This is a perfect example of that, right? We have east. We have east labeled there. By rights, we should, always. We get a negative value there. What does that mean? It means to the west, right? If we had have made this position west and we got a negative value, what would that negative have meant? It would have meant east then, right? So you can write in the negative, leave the negative, or you can write in the word east or west, or whatever the case may be, whichever works for you. The average velocity of the object in the graph between 0 and 10 seconds, well, the average velocity is going to be displacement over time. We just found the displacement. It's negative 50 meters. The time between 0 and 10 is 10 seconds. So we're going to say it's negative 5 meters per second. Negative 5 meters per second. But the formatting of this isn't great. Just notice. What's the instantaneous velocity at 2 seconds? Is it a straight line? Is it constant velocity? All right, if it's constant velocity and the average is -5, then what's it going to be right here? -5. 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 It's going to be -5 meters per second everywhere. What's it going to be at 7 seconds? -5 meters per second. Is that okay? Hey, making some sense here? All right, here's what I want you to do for homework. On your worksheet, please do, there's 4 questions on that sheet. Please do the first 3 questions for homework, please.